Hello, thanks for joining us today. In this session, we're going to be talking about how we can do percentiles at scale. We'll touch over why we need percentiles and how we managed to enable this in Druid and querying over trillions of rows at interactive speeds. My name is Ben Sykes. I'll be presenting with my colleague, Samath Jain. We're both software engineers at Netflix working with data. First of all, why do we need distributions or percentiles? Well, averages don't tell the whole story. This data set here is a fake data set, but let's pretend it represents the page load time of a particular website. As you can see from this chart on the right, the mean isn't really representative of the main distribution. It's not representing most of the actual samples that contribute to this measure. If we were to use this mean alone, it would be really misleading to try and improve that value or even alert on it if it were to regress. Even if we were to take just the median, for example, the 50th percentile there in the middle, all that's going to tell us is that half of the events are better and half of the events are worse. But it doesn't really tell us how much better or how much worse. If we want to try and improve this measure, then we really need to look at the whole distribution. Otherwise, we may be harming some of the users that have a terrible experience at the expense of delivering a better experience to some of the people who are getting currently a faster page load, perhaps. Taking those single points, either the mean or the median, only give you a snapshot of a very small population there. So the reason that the mean here is so much higher than the median is that this data set has a massive tail. So we plotted up to the 95th percentile here. If we were to 99, you can't see the rest of the chart. It just looks like a flat line because the tail is so long. So the mean can be heavily influenced by these extreme outliers on either end, actually. More so in this case on the long tail. So having a distribution here really helps us understand how all of the population is experiencing this page load. So how can we store distributions or percentiles in Druid? We have a few options available to us, either as built-in modules or as extensions. So we'll take a look at the common ones: tdigest, datasketches, and specifically a quantile sketch within that, and our current in-house version, Spectator Histogram. So the main thing here is tdigest is just too slow to be really interactive. It's too big storage-wise. It is accurate. It is accurate enough to be useful. Datasketches, they are fast. They can be queried at interactive speeds, but they're still too big. And again, accurate enough for most of our use cases. So we looked at Spectator Histogram to try and solve that too big problem. So we made it fast, we made it small, and still accurate enough. And Samath will drill into some of the details about how this compares with the other options later on. So how can we turn a distribution into something that we can store in Druid? Our data is rolled up to the minute grain. So all of the samples that arrive within a minute can be collected, collapsed into a single distribution. So this is where the approximation comes in. These aren't true percentiles and they're not true distributions. We're effectively saying that any two values or any multiple of values that land into that same bucket are effectively the same number. If we can make these buckets appropriately sized, then we can get a very good approximation. By turning them into these buckets, we can then represent them in Druid relatively easily. So we do this by converting these distributions into counters. So we take that histogram, that distribution, and we say that, for example, minute 1 here, 2 of the samples are in bucket 1. and I'll explain what the buckets mean in a moment. But having these as counters, so we've got bucketized counters, we can then aggregate these very easily. So this is assuming that the bucket ranges are consistent across all of the samples that we have here. And we can enforce this because we designed the bucketing scheme, which I'll talk about in a moment. With T-Digest and some other histogram bucketing systems, this is not necessarily true, which means that when they try and query and merge, they have to recompute what the bucket ranges are for that data set. This can really hamper query performance. We use the Spectator bucketing scheme. This comes from an internal in-memory time series database called Atlas. We borrowed the same scheme for the primary benefit of someone else has already done the research to say that these buckets are accurate enough, but also it works with all of our existing internal tooling, which makes the transition from the Atlas dataset to the Druid dataset seamless to most of our users. So Spectator uses 276 buckets spanning the entire 64-bit number space from 0 to long max value. So it should be noted that this means that we have to use longs for our data and they cannot be negative. The buckets themselves are not fixed in size. They vary from individual values all the way up to huge values at the other end. So this is really, it's deliberate so that we can have better accuracy when the numbers are smaller. For example, with timers, knowing whether you're a few nanoseconds off, the accuracy is kind of important there. But when you're getting up to the days or even the years, then being hours off or even days off at that point really probably doesn't matter all that much. So we get this nice accuracy for the smaller numbers. We can be within milliseconds, we can be within microseconds even, and have a decent amount of accuracy there. So this is almost fixing the error bound versus fixing the bucket size, which would be the absolute error. So to store this efficiently in Druid, we came up with our own data type, the Spectator Histogram. Every value in that column is in itself a Spectator Histogram instance. And this histogram can store the entire histogram for that row. So it can have multiple entries in it. We store this effectively as a map. So we'll have the key is the bucket ID, and the value is the count of entries in that histogram column. So for this example here, where we have a few samples, we have a sample of real measure 10, real measure 30, we've got 3 counts of the 40, 2 counts of the 50, and 256 counts of the 100. So this can be represented as the map in a JSON format on the right-hand side there. So value 10 falls into bucket ID 10 because we have individual buckets for these very small numbers. Value 30 actually falls into bucket 17 because we started to get a bit of range on these buckets now. And by the time we get up to value 100, then that's bucket 25. You can see that the range for that bucket is 85 up to 106. So what we're saying there is that any value between 85 and 106, we're going to treat the same. It's that whole bucket. So one of the benefits that we were really pushing for when we're designing Spectator Histogram was the size. So we already had a fast implementation looking at datasketches, but we really wanted to make the size, the storage size, as small as possible, or as small as practical, while maintaining that query performance. So we use a bit packing format to represent this histogram, this map, in a very concise way. So for the 276 buckets, we can represent that with just 9 bits. So we take some 9 bits from one of these bytes for the bucket ID. We then use the rest of those values, the rest of the remaining bits in the top 16 bits as a set of flags. And in some cases, when the count is very low, we actually have enough bits there left over to do the count as well. So for a simple entry in the histogram, we can get away with only 16 bits. For bigger values, or bigger counts, I should say, we sometimes need to split out into additional bytes so that we can have bigger counters there. And we'll use the flags in those top 16 bits to say how many bytes we're going to be using for the count. So we can have a single byte, we can have 2, 4, or 8 bytes. So we can do up to full long max value of counts as well. So for this histogram here that has 263 entries, we can represent that in just 12 bytes using this bit packing format. So I'll hand over to Samath now, who's going to talk about how these compare with tdigest and datasketches. Over to you, Samath.
Thanks, Ben. Next, I'm going to talk a bit more about the evaluation that we did for comparing Spectator Histogram with other approximate percentile implementations that we have in Druid, specifically tdigest and datasketches. We ingested the exact identical data into three data sources. One data source stored the distribution as tdigest, the other stored as a histogram, and the last as datasketch. We had over 7 days worth of data stored at a query minute granularity. Our evaluation involved issuing queries against each data source, one data source at a time, over thousands of iterations. Because we utilize caches on historicals, we wanted to make sure that we are randomizing the intervals that we are using in our queries and the dimensions that we're grouping by, just to make sure that we're invalidating the cache and sort of mimicking what you would see in real world scenario. The graph here, x-axis is pretty self-explanatory. The x-axis is the query interval, y is the query response time. As you can see, as the length of the query interval increases, the tdigest performance gets worse and worse. In fact, if you look at the min and the max of the response times, it gets up to like 3x worse. On the other hand, for Spectator Histogram and datasketch, the performance actually doesn't get that bad, right? And more importantly, the Spectator Histogram query time is actually quite close to the datasketch query response time. Ben already talked about this, or at least alluded to, because we use variable bin packing, how we can optimize for the data size. And this gets illustrated, here. You will see that the data source for the Spectator histogram is almost like 60% of the size of datasketch, and 50% of the size of tdigest. And imagine scaling this over. And over here, we stored only one particular percentile column or one distribution column, right? Imagine having hundreds of such columns and trillions of rows, right? These size savings then start becoming significant. So histogram so far has performed well in terms of query performance, in terms of storage size, great. But then if the results are not accurate enough, right, then it's not a good fit for us. So the way we went about measuring the accuracy was we took the data set, sorted it, and then we computed the exact P10s and P20s and P30s, etc. Right? And then we asked each of these data sources, give us back your approximate P10, P20, and we just charted them out, right? Just to see what is the relative difference between the percentile values reported by them. And as you can see here, on the graph, they actually are quite good. The approximate percentiles are pretty much what the actual values are, except for quantile sketch, where during the P99, at least for our data set, it gets a little bit error prone. Zooming into this a little bit more, this is what the next graph shows, is the error percentage, right? And here you will see that for quantile sketches at P99, the errors were around like 5.5%. T-Digest and Spectator Histogram, the error didn't go beyond like 2.5% or so. So accuracy-wise, these two perform the best. So there's another way of looking at this. If your organization uses T-Digest heavily, for example, Netflix uses T-Digest heavily, right? And then if you were to look at, how different will be the percentile values reported by Spectator Histogram versus what T-Digest has been reporting it, then you will see that, it doesn't actually vary that much. Spectator Histogram, the results reported are like, what, 2.5% in the range of what T-Digest reported, right? There's a more variation when it comes to quantile sketches and T-Digest, right? And again, it's because the quantile sketch performance suffers at P99s. For our data set, we see this difference. So in summary, right, what we see is that Spectator Histogram, is actually an excellent option for us. This data size is significantly lower. What it means that we will need less amount of memory for storing the same amount of data in terms of number of rows, or alternatively, we can fit more into the page cache of historicals, or we can potentially save some cost and scale down historicals, right? The query performance also, it closely tracks the data sketch query performance. And remember, and this is at like the 60% of the storage size. Accuracy wise, also, again, it's comparable, sometimes better than quantile sketches, especially at the higher percentiles. For sure, T-Digest actually turned out to be the slowest. So it probably, at least for T-Digest, we can see that Spectator Histogram could be a good replacement here. In general, though, this is one point I wanted to make here, that data sketches are a great choice. They're widely adopted industry standard here, and they are like sort of the default percentile implementation that in Druid, right? But then once your data size, or once the number of rows goes beyond like trillions of rows, and then you have to store tons of data, then data size or the sketch size starts becoming important, right? And which is where Spectator Histogram provides a good fit. So if you have those kinds of scenarios, I would encourage you to try out the histogram implementation. So what's next, for us? So the current implementation that we have, it is not vectorized. So we would definitely like to implement the vectorized aggregators, and hopefully that should bump up our query performance even more. We would like our users to be able to use them in their Druid SQL queries. So we would like to add the SQL functions for them, SQL aggregators and post aggregators. And of course, we understand that folks in the community would at least like to try out the Spectator Histogram implementation. So we would like to contribute to upstream, so other folks can try it out, use it, provide feedback, and have the community just maintain it going forward. Right? Thank you.